Hi there. Hello, calculus class, students, people. So today I want to talk a little bit about how we measure velocity. So this is from section 1.1, velocity. And I want to begin with an example. Imagine that you're on top of let's say a building. So here you are on top of the building, and in your hand you have a tomato. Here's your tomato. And your plan is to heave this tomato off the what a retarded tomato. To heave this thing off of the top of the building and send it crashing into the pavement below. So down, down, down it goes until it squirts all over the sidewalk. So let's suppose that the building is 64 feet tall. 64 turns out to be a number that's pretty easy to work with here. So a 64-foot tall building, and using a couple of things that we know from physics, we can write the function that gives the height of the tomato, s of t equals 64 minus 16t squared, gives the height of the tomato in feet, where t is measured in seconds. So the first thing that we could do is answer the question, how long does it take the tomato to hit the ground? How long till the tomato hits the ground? So we're looking then for the value of t, right? Because we want to know the time that it's going to take. So let's see, we know that time is equal to 0 up here when we let go of the tomato, and we want to know what time is it down here. We know that s up here, the height of the tomato, is equal to 64 because it's there with us up on top of the building. And if you make t here equal to 0, s is equal to 64, right? So what is s equal to down here? Well, when the tomato is on the sidewalk, s is equal to 0, right? So we want to solve 0 equals 64 minus 16t squared. And this is a pretty easy algebraic equation. 16 happens to go evenly into 64. It goes 4 times, and if we take the square root, we get t is plus or minus 2. But of course, the negative 2 doesn't really apply here because the whole thing begins when t is equal to 0. So we get t is equal to 2. So the answer to the question, how long until the tomato hits the ground, is t is equal to 2. The other question that we have is this one. What is the velocity of the tomato at the instant that it splatters? And I guess another way to think about this is, if you were in your car and you drove your car into a brick wall, as soon as you get to the wall, your velocity is equal to 0, but at the instant that you hit the wall, you could look at the speedometer, which might very well be the last thing that you see, right? Because you're crashing into a brick wall. And you can say, oh, I was going 60 miles an hour when I crashed into that brick wall. So if the tomato had a speedometer on it, what would the reading be at the instant that it hit right here? We don't really have the tools to answer the question, but what we can do is examine the average what are some average velocities near t is equal to 2. So if you recall from the reading, the average velocity between t is a and t is b is given by s of b minus s of a all over b minus a. So what if we looked at what was the average velocity in the last second? So what would that be? That'd be Avg 1,2, right? So s of 2 minus s of 1 divided by 2 minus 1. The 2 minus 1 part is easy, right? 2 minus 1 is equal to 1. S of 2, we already know what S of 2 is, right? Because when t is equal to 2, S is equal to 0. It's right here. So S of 2 is equal to 0. What's S of 1? Where can I do that? S of 1 is 64 minus 16 times 1 squared. 64 minus 16 is 48. So you get 0 minus 48 over 1, which is equal to negative 48. And this is going to be in feet because that's what S is measured in per second, because that's what these times are measured in. So negative 48 feet per second. It's negative because the tomato is falling. It's not going up. So there we have the average velocity over the last second. How about in the last half a second? So that's the average velocity from in the last half a second. That means we want time to go from 1.5 to 2, right? So we need s of 2 minus s of 1.5 divided by 2 minus 1.5. S of 2 is still equal to 0. Do I have a calculator here somewhere? I don't know if you'll be able to see this. I'll just do this real quick. Clear. 64 minus 16 times 1.5 squared. Good Lord, it's dusty. 28. So 0 minus 28 all over 2 minus 1.5 is 1/2. So negative 28 divided by 1/2 is negative 56. And this is in feet per second as well. So we could continue like this, closing in on this interval. Like we can ask, what about in the last tenth of a second? Avg of 1.9, right, up to 2. S of 2 minus s of 1.9 divided by 2 minus 1.9. 0, let's see, this is going to be 0.1 on the bottom. Uh, 6.24 minus 6.24, negative 62.4 feet per second. So we could continue on like this, taking a smaller and smaller interval, and with a calculator we can really, we can make this 1.99999, right, and get really close. In fact, let's do that. So in the last 0.0001, oh yeah. So what'll that be? How many nines? 1, 2, 3, 4. Let's see what we get from this. S of 2 minus S of 1.9999 over 2 minus 1.9999. One, two, three, and then square it. 0 minus 0.00639984 divided by 0.0001 divided by 0.0001. 63.9984. Negative 63.9984. So, if this is what we get when we're in the last, what is that, 1/100,000th of a second, what do you think the actual speed of the tomato was at the instant that the tomato hit the ground? Yep, me too. We think the final velocity and we will see that this is there's me thinking. We'll see that this really is the right answer, and we'll look at ways that we can take the work that we've done here and sort of generalize it and apply some really cool calculus ideas to it that will get us to this point much more quickly. Stay tuned.